Okay, thanks to everyone for being here. I'm very happy to be here in Pasto. This is my first time. So today I'm going to talk about the proving low reheating scenarios with minimal freezing dark matter at the volcano Cumbal. So the conclusion that is that this freezing mechanism works at least for human beings. Okay. Good. So this work has been done in collaboration with Nicolas Bernal at New York University in Abu Dhabi and Sheng Feng in ABC University in Rio, in Brazil. So this work is going to be published on arXiv, I hope, this week. So the outline of my talk comprises a brief introduction to the WIMP and basically to the FIM mechanism. Then I will discuss the so-called minimal freezing model. Then I will discuss the reheating dynamics and how the reheating affects the prospects for the dark matter abundance. And then I will discuss our main results. We will consider two cosmological scenarios, one where the radiation dominates the universe at the very early time, and the other one is the actination domination. I finally will conclude. So I hope to not have to convince you that the evidence for dark matter is abundant and compelling. So we know that the dark matter must be massive, neutral, and stable. And despite of this evidence, we don't know what is the nature of the dark matter particle. So the most well-studied candidate is the WIMP particle. This kind of particles, they are weakly interacting massive particles. So this means that they reach the thermal equilibrium with the standard model plasma. So in other words, this kind of reactions take place in both ways. So dark matter are produced and then annihilated into standard model particle and vice versa. So the WIMP miracle, the idea behind the WIMP miracle is that for if the dark matter particle has weak interactions, so interaction of the type of the weak interaction scale, and also masses around the weak scale, so we can easily describe the correct dark matter abundance. So this is the WIMP miracle, and this kind of the WIMP mechanism relies on the chemical freeze out that has played a role also in the formation of the CMB and also in the formation of the light elements. So this means that the chemical freeze out has been used not only once, but twice in nature. So nature knows about chemical freeze out. So this is, in my opinion, why the WIMP mechanism is so appealing. However, as we have has been shown in the previous talks, the WIMP paradigm is not free of challenges. So we have theoretical and experimental challenges. So maybe the dark matter is not composed by WIMPs. Okay, and with this idea, we want to explore other alternative mechanisms. So in this case, I'm going to focus in the FIM mechanism. So basically, here in this scenario, the dark matter is composed by FIM particles. So they are feebly interacting massive particles. And due to the feeble interaction with the standard model, so these particles do not achieve the thermal equilibrium. So this term in this equation basically is neglected. So this means that the universe is populated with dark matter particles thanks to either inverse decays of standard model particles, also decays of standard model particles into dark matter particles, or via standard model particles, scattering of standard model particles. Notice that in this case, the dark matter mass could be ranges are several orders of magnitude. So there is no a specific mass region. And the main drawback of this kind of mechanism is that it's very difficult to test it, okay? Because the interaction between the dark matter particles and the standard model is so negligible. It's quite small. However, as David showed us, there are some recent developments that actually some experiments are currently proving the more simple film scenarios. Notice, for instance, this is the projected sensitivities of Sensei, Damic, and Oscura experiments on the elastic cross-section of dark matter with electrons. So notice that we have an improvement by several orders of magnitude. And from in the experimental side, this is a huge step. So now I'm going to discuss the minimal freezing model. This model basically is a gauge extension of the standard model. So this means that we introduce a U1 gauge symmetry with a very light gauge boson X mu. Okay, keep in mind that this guy is very light. Very light means for us in this scenario, masses lower than 10 to the minus 21 MeV. Okay, 10 to the minus 21 MeV is quite light. This is because in this way we can evade a lot of constraints. The second ingredient is a Dirac fermion. So basically, this particle is the dark matter particle, a Dirac fermion, with a charge E prime and no standard model charges. So it's a singlet under the standard model gauge group. Okay, and all the standard model particles do not have a charge under this U1 gauge symmetry. Okay, it's quite simple, this model. And with these ingredients, we can write down the Lagrangian that involves the kinetic term for the hidden photon. This guy, we name it hidden photon because it's like a photon in the dark sector. So this is the hidden photon. So this is the kinetic term for the hidden photon. This is the mass term for the hidden photon. This is the kinetic and mass term for the Dirac fermion. This is the interaction term between the dark matter particle and the dark photon. And finally, this term represents what we call it the kinetic term. So it's a kinetic mixing between the hypercharged gauge boson and the dark photon. Okay, this is the kinetic mixing portal. And notice that this term by itself is gauge invariant and also this term. So this is the reason why this term must be present in the Lagrangian. Okay, so after the electroweak symmetry breaking, we identify the mass eigenstates as always. And we end up with A. A is the standard model photon. We have A prime, that is the dark photon, and the Z. And in the mass basis, this is the Lagrangian of the model in vacuum. Notice that involves the interaction between the dark matter and the hidden photon with a charge E prime. Notice that the dark fermion, the dark matter particle, also interacts with the C boson. But notice that the charge, the coupling is given by the product of the E prime and epsilon. And epsilon in this scenario, in order to implement the freezing mechanism, we need to impose that epsilon is quite small. Small as, let's say, 10 to the minus 7 or below, okay? And notice that the electromagnetic current also couples to the dark photon. but in this case with a electric charge that is suppressed by epsilon, okay? And this epsilon is, again, below 10 to the minus 7. This is the vacuum Lagrangian. We know that due to the interaction of the standard model photon with electrons, the photon acquires a mass. This means that in a plasma, photons becomes massive. And the mass of the photon is of the order of the temperature of the plasma. And due to this mixing between the photon and the hidden photon, the dark photons also gain a thermal mass. So this means that we need to construct the Lagrangian in medium, and at the end, in a medium, we know that the electromagnetic current coupled for sure to this is the visible photon, our photon, the standard model photon, and also to the hidden photon. But notice, however, that depends on this mass ratio. And since we are considering very low masses for the hidden photon, basically this term becomes quite suppressed. So at the end, what is the message behind this analysis is that hidden photons are not produced during in the early universe. So the production of hidden photons is suppressed. So in other words, we can ignore them in the early universe, the hidden photons. Good. So this kind of model can be proved in experiments thanks to the interactions of dark matter particles with electrons. And notice that in this case, the elastic scattering concentration with electrons depends on only, for sure, depends on the electron mass. This is the electric charge divided by 4p, etc. But also depends on kappa. And this kappa is the product of E prime and epsilon. So these are the two free parameters that combine in one single parameter. So at the end, the cross-section depends only on kappa. So, and the dark matter is produced in this scenario thanks to the fermion annihilations, thanks to the C boson decay into dark matter particles, and also thanks to the plasmon decay. This plasmon decay is when the standard model photon acquires a mass. So in this case, the photon can decay because it has a mass, okay? And basically, since we are considering this upper bound for the hidden photon mass, so basically this scenario is basically the same scenario of the massless with a massless hidden photon. So basically, our scenario contains two free parameters: the dark matter mass and this coupling kappa that enters not only in the direct detection cross-section, but also in the relic abundance. So at the end, we can prove the viable parameter space compatible with the Planck constraint, Planck measurement, sorry. So in this plot, the y-axis represents kappa. Notice times 10 to the 11. So this means that kappa must be of the order of 10 to the minus 11, okay? As a function of the dark matter mass. The black line corresponds to the line to the points that explain the correct dark matter abundance, okay? Notice that here we have them, basically, here we have them, the dark matter mass is equal to the mass of the electron. So this means that below the electron mass, the main channel contributing to the dark matter abundance are the plasmon decays. From here to here are the fermion annihilations. In this point, sorry, from here to here, and then from here to here we have the Z decays, and again here we have the fermion annihilations. The blue regions, The blue regions are excluded regions by direct detection experiments, in this case by Sensei, and this is by LZ. And these constraints coming from astrophysics, actually, namely by cooling, concept coming from the star cooling. And notice that the dashed line, this dashed line, and this dotted line represent the project sensitivities of the Oscura experiment. So this experiment will probe basically all the parameter space, almost all the parameter space compatible with the dark matter abundance. So this is, in some sense, quite unique, that one experiment will basically probe all the parameter space of your model. So this is a, I would say, kind of dream of a theorist, okay? So, but now I'm going to discuss the reheating dynamics. So reheating is, it is generally assumed that the reheating period is preceded by a cosmic inflationary epoch. So basically, we have that after inflation, we have a reheating epoch, okay? So notice that in this case, in the y-axis, we have the Hubble co-moving distance as a function of the scale factor. So basically, during inflation, the Hubble co-moving distance decreases, and then we have the reheating epoch, then the radiation dominated era, then matter domination, then the dark energy domination, and basically we are here, okay? So usually people assume that the reheating is instantaneous. So the duration of the reheating is basically 0. So we pass from inflation to radiation domination instantaneously, okay? So this is the standard assumption. However, we know that particles have, decaying particles have, has a finite lifetime. So that is the idea behind this work. We are going to consider a non-instantaneous inflaton decay. And this reheating, so the cosmic reheating period can be approximated by different inflaton potentials. For concreteness, we are going to consider only monomial potentials 5 to the some m power. And it's important to know that these reheating potentials only apply for this region. This region is the inflation era. Okay, we have a potential during this era and another potential for this era. But it's also possible to have a unique potential that describes both phases. And these are for example, the so-called alpha attractor T model. For example, this kind of model. Notice that for large values of the field, that we have a constant value for the potential that is what you need during inflation, and a monomial potential for small values of the field. Okay, so during reheating, we have that the inflaton oscillates in this potential. The equation of state omega is the ratio between the pressure over the energy density, and notice that goes as m minus 2 over m plus 2. Notice that for n equal to a quadratic potential, we have that omega is 0. So omega is 0 means that the inflaton behaves as matter, okay? But in general, at the end, the energy density scales, depends on the scale factor as 1 over a to the 3 times 1 plus omega. Again, omega equals 0 is the standard scenario. So the inflaton behaves as matter, but remember, it's not necessarily in that way. And due to this, due to the oscillation of the inflaton oscillation in this potential, we have that the Hubble rate scales in this way during reheating. So it depends on the equation of state of the inflaton. And regarding the radiation, the standard model plasma. So under this kind of dynamics, we don't know how. So it depends on the specific. I would say. We don't know what is the behavior, the background of the standard model plasma, so we can parameterize it in this way. The temperature as a T reheating temperature times the scale factor to some power alpha. We know here T reheating denotes the standard model temperature, the reheating the value of the when the reheating ends. And notice that the T reheating is when the inflaton energy density is transferred to the standard model energy density. And this temperature must be larger than 4 MeV, that corresponds to the temperature where the light elements were formed. So by considering a non-instantaneous reheating, so basically we have two more free parameters, alpha and omega. Okay, omega is the equational state of the inflaton, and alpha represents the variation of the temperature with the scale factor. We are going to consider only matter and kination. Matter is omega equals 0 and alpha equal 1/2, and also 3/8, and kination omega equal 1. So this is the previous plot, but assuming that the reheating temperature is not quite large. In this case, is, for example, 10 to the -1 GeV, 10 to the 1 GeV, 10 to the 3 GeV, 10 to the 5 GeV. So this means that this line is converted into this one, this one, this one, or this one. So by this means, in other words, by reducing the reheating temperature, we can allow for larger values of the coupling between the standard model particles and dark matter particles. And notice that the current experiments are actually proving these non-standard cosmologies. Okay. Now I'm moving to when the case of non-instantaneous reheating. In this case, these lines are converted into bands. So these bands are obtained by maximizing the maximum temperature reached by the standard model sector. And notice the measures at the end is the same. So basically, the reheating, a non-instantaneous reheating, allows us to have larger values for this coupling kappa. This is for matter domination, and finally for kination domination. Notice the impact is remarkable. So the freedom on choosing kappa for a specific to describe the correct dark matter abundance, so is quite large. So, however, we can now the experiments are now proving a lot of part of the parameter space. So for these lines again are for different reheating temperatures. So the idea here is that by considering a non-standard cosmology, we can allow for larger couplings of the dark matter between the dark matter mass and the dark matter particles and the standard model particles. But the important thing is that the experiments are actually proving this kind of non-standard cosmological scenarios. Finally, notice again the future sensitivity of Oscura and also this line. So basically, this experiment is proving the dynamics of the universe at very high temperatures. Okay, that is it. Thanks for your attention.
So, yeah, you're open for questions. Let's start with Diego.
From what
assumption you need to have the dark photon as small as you use?
Because there are constraints coming from astrophysics. So, because in that case, for example, stars can so reduce their temperature much quick that as usual. So these constraints of a mass for the hidden photon below 10 to the minus 21 MeV comes from that fact, and also that the CMB is not affected because you have interaction between. Sorry.
In which context? Dark photon in film scenario?
Right. This is for film scenarios, right?
Question here.
Hi, Professor, and thank you for your talk. I have just a small question. Why do you only consider monomial terms in the inflaton potential?
Just for simplicity.
Okay.
But for sure, you can construct, I would say, more elaborated potentials. But as we know, we can expand it in terms of powers, ponomials, right? Yes.
So, Oscar, what kind of experiment is this Oscura you mentioned?
This experiment, by the way, is from people that compose that belongs to Sensei, and the leader of this experiment, Oscura, if I am not wrong, is Juan Estrada. This is an Argentinian guy, and basically is made. Basically, all these experiments are based on CCDs, so cameras that are tracking an electron, and they can track one single electron. And in principle, the number of CCDs will around 50,000. So, and this kind of experiment are tabletop experiments up to some point. Okay. So maybe David can say more about this.
Yeah, essentially what you said. Yeah, they're combining technology that they already know that works for a single CCD, both dynamic sensei and super CDMS on a surface experiment. They tested that, and the idea is to it shitloads of things.
Any other questions?
Actually, since I'm, is there any way that you can go? I mean, if you go to one of the, I think it was one of the latest slides. Okay, everything really you're moving above the line of freezing. Is there any way you can go down? What can you do?
To go down.
A consistent model below that line.
No, so within this, for all these possible of values or alpha and omega, it's not possible.
Not like this, yeah. But if I wanted to, yeah.
Yes, we will trying to come up with to reduce the value of kappa, but we didn't. So.
Okay, thanks, Oscar, again.
Bueno, muchas gracias. Yo les voy a hablar sobre la producción de materia oscura a través de la fusión de gluones. Este trabajo está siendo dirigido por los profesores Edilson Reyes y la profesora Blanca Cañas. Está dividido en 3 partes. Vamos a hablar sobre la motivación, los cálculos prioritarios para poder hablar de producción de materia oscura y las perspectivas futuras de este trabajo. Inicialmente, recientemente Atlas y CMS han estado dirigiendo sus búsquedas de los decaimientos invisibles a través de los datos de los ciclos realizados por el LHC, el ciclo 1 y 2, tratando de buscar evidencia de materia oscura. Sin embargo, no ha sido posible encontrarla, ¿no? Dando ellos como una conclusión con un 95% de nivel de confianza que no más del 13% de los bosones de Higgs producidos en el LHC pueden transformarse en partículas invisibles. Esto impone límites claros sobre futuras observaciones en los aceleradores y además sobre los modelos teóricos que se que tratan de explicar este fenómeno. Aquí podemos observar una reconstrucción de una detección de un jet, emitido por un proceso de posible canal de producción de materia oscura. Quedamos a la expectativa de obtener resultados concluyentes sobre este tema, ya que, como sabemos, hay suficiente evidencia que explica la existencia de la materia oscura. Una de ellas, que es la más conocida, es el tema de la rotación de las galaxias en los cúmulos, la cual es superior, la observada es superior a la teórica, y la única manera para que estas estructuras se puedan mantener unidas es que exista más materia. Y la explicación sobre esto es la existencia de materia oscura, ¿sí? Hay otras explicaciones sobre esto, pero sin embargo la más aceptada actualmente es la existencia de la materia oscura. La detección de materia oscura no es directa, se hace de manera indirecta a través de este canal, específicamente de la fusión de gluones. Primero hay una fusión de gluones que está mediada por un loop que genera un Higgs, y posteriormente este Higgs va a decaer en materia oscura. Sabemos que existe un 84.4% de la densidad total de materia en el universo es materia oscura. Por eso es importante tratar de dar explicaciones sobre estos posibles canales de producción y que son los que se están estudiando en los colisionadores de partículas. Este tipo de detección no es un tipo de detección directa, como lo han venido explicando anteriormente, ¿sí? Sino una detección por parte de colisionadores. Nosotros nos vamos a centrar en el canal principal de producción del Higgs, el cual está mediado por un quark top, dado que es el más masivo a comparación con el resto de las demás partículas, ¿sí? Centrándonos en el cálculo principal de la sección eficaz de producción del Higgs y luego haciendo un estudio sobre los análisis que realizó el LHC sobre la estadística para la posible producción de materia oscura a través de los decaimientos del Higgs. Para esto vamos a construir un lagrangiano que contenga la interacción entre los gluones y los quarks y el Higgs, considerando entonces el lagrangiano de la QCD y un lagrangiano tipo Yukawa que contiene la interacción entre el Higgs y los quarks. Identificamos el lagrangiano de interacción y procedemos a hacer el cálculo mediante la matriz S, los elementos de la matriz S. Sin embargo, para hacer el cálculo de la amplitud de probabilidad, que es la que vamos a necesitar para posteriormente hacer el cálculo de la sección eficaz de producción. Sin embargo, realmente no conocemos una solución exacta para calcular estos elementos de la matriz S y procedemos a aplicar una expansión perturbativa sobre este elemento, ¿sí? Reescribimos este elemento en términos de los momentos iniciales y finales y nos notamos que cuando aplicamos el teorema de Wick, la contribución de orden dominante aparece en el cuarto término de esta forma, ¿sí? Y solamente los elementos que contengan este tipo de estructura son los que van a contribuir. De ellos saldrán 3 elementos, de los cuales solamente tendrán 2 posibles contracciones distintas que generan la contribución a este proceso. Una vez tenemos identificado estos elementos, haciendo contracciones podemos calcular la amplitud de scattering. Para comprobar el resultado de estas contracciones, consideramos las siguientes reglas de Feynman, ¿no? Donde tenemos el vértice de interacción del quark con el gluón, del quark con el Higgs, los propagadores fermiónicos y los gluones entrantes, que generan sus respectivas contribuciones. Y procedemos a construir la amplitud de probabilidad. Notamos que existen 2 diagramas que generan una contribución, que visto solamente como diagramas de Feynman, notamos una diferencia en los estados de helicidad de los gluones entrantes. Sin embargo, al hacer algunos shifts sobre los momentos de loop y los estados de polarización, podemos reescribir estas dos contribuciones como una misma, así que es necesario hacer como, tomamos una y la multiplicamos por 2 porque va a dar el mismo resultado en la contribución. Una vez construimos la amplitud de probabilidad, la amplitud de scattering, lo que procedemos a hacer es a resolver los elementos dentro de la integral de loop, que son los que necesitamos para poder encontrar la solución de esto. Inicialmente, esta contribución es finita y para poder mostrarlo nos vamos a aplicar una regularización en d dimensiones y procedemos a resolver lo que es la traza del numerador aplicando el álgebra de Dirac y posteriormente reescribir el denominador en términos de estos elementos. Lo reescribimos de esta manera con el fin de construir o reescribir la amplitud de probabilidad como un conjunto de integrales que son conocidas como las integrales de Passarino-Bellman o las funciones de Passarino-Bellman, las cuales se dividen en funciones tensoriales de rango 0, 1 y 2. Las de rango 0 son conocidas como funciones de Passarino-Bellman escalares que tienen sus soluciones bien conocidas y bien definidas. Y las funciones de Passarino-Bellman que no son escalares, se les aplica un método de reducción de Passarino-Bellman para tratar de reescribirlas en términos de funciones escalares. En nuestro cálculo es posible hacer esto, no necesariamente siempre se puede hacer este tipo de reducciones, eso depende del tipo del proceso que estemos llevando, los momentos externos y cómo esté conformado el diagrama como tal. Estas funciones de Passarino-Bellman pueden ser reescritas en términos de letras que van asignadas dependiendo del número de denominadores que tengan. Si tienen un denominador, se les asigna la letra A, si tienen 2, la letra B, y si tienen 3, la letra C. En este caso, esta sería como un C sub 0, y las que no son de rango 0 conservan el índice de Lorentz para mantener la invarianza. Reescribimos entonces la amplitud de probabilidad en términos de las funciones de Passarino-Bellman, como observamos acá. Aplicamos la condición de transversabilidad de los gluones, de los estados de polarización en los gluones, y notamos que los que generan contribución sobre este proceso principalmente son este término y este término que observamos acá. El resto se tienden a cero, y este término que tenemos acá. El resto tienden a cero. Una vez tenemos esto, en este término se aplica el método de reducción de Passarino-Bellman, que no es más que reescribir esta integral tensorial en términos de unos cofactores y los momentos externos de loop. Estos cofactores vienen dados de esta manera con sus respectivos índices y se calculan a través de construir un conjunto de ecuaciones. Este elemento que está acá contiene la divergencia, pero se ve suprimida por el cofactor que está acá, que está en términos de funciones escalares de Passarino-Bellman, ¿sí? Una vez ya conocemos estas funciones de Passarino-Bellman y los cofactores que han sido calculados, procedemos a resolver la amplitud de scattering. Esto se puede resolver aplicando directamente los valores ya conocidos, pero también se puede hacer por medio de un proceso, un algoritmo desarrollado en matemática que utiliza programas como lo son FeinArt, FeinCal, FeinHelper, y nos da la siguiente solución. Una vez tenemos la amplitud de probabilidad, procedemos a calcular la amplitud de scattering al cuadrado y hacemos la suma sobre todos los estados de polarización, dado que tenemos un gluón. Es un poco diferente a los fotones porque el gluón contiene una carga de color a diferencia de los fotones. Una vez tenemos el resultado de la amplitud de probabilidad de scattering, si consideramos las siguientes sustituciones y reescribimos la constante de acoplamiento de Yukawa en términos del valor expectante del vacío, podemos reescribir esta amplitud de scattering de esta manera si consideramos la relación que hay entre los logaritmos complejos y los arcosenos a través de métodos algebraicos. Una vez tenemos ya la amplitud de probabilidad al cuadrado, lo que procedemos es a calcular la amplitud de scattering, que nos queda en términos de un tau, con un tau mayor o igual a 1, para que pueda tener la relación con, esta función. Entonces nos preguntamos, bueno, esta sección eficaz de producción que hemos calculado, ¿cómo la podemos relacionar con estos decaimientos invisibles? Como bien había explicado anteriormente, este proceso que está acá es el que estamos estudiando, y si este proceso se da de esta manera, sería invisible ante los detectores, ¿no? Entonces es necesario, o lo que hace el LHC es centrarse en un subconjunto de este proceso, el cual emite un jet gluónico, y este jet gluónico, a partir de este jet gluónico es que se hace la reconstrucción de este proceso como tal, de producción de materia oscura. Este jet gluónico contiene la información, está bien identificado, los diferentes grupos, los diferentes experimentos los tienen bien identificados sobre los jets cuárquicos que también existen, o a veces que salen dos jets de otro tipo de proceso. Este es uno de los tantos canales de producción de Higgs y que pueden decaer en materia oscura. Sin embargo, existen otros a través de lo que es la fusión de bosones vectoriales, ¿sí?, que generan diferentes procesos. La fusión de gluones que generan posibles decaimientos de Higgs en materia oscura tiene dos canales. El principal que estamos estudiando nosotros es este, pero existe otro donde acá, en vez de que el top se cierre acá, lanza dos top libres que hadronizan y generan dos jets que pueden ser identificados. Sin embargo, nosotros nos centramos en este. Para poder hacer esta reconstrucción se requiere de una sección eficaz inclusiva de precisión. Aunque nosotros hicimos el cálculo al orden dominante, ya, pues, como va avanzado, se hace hasta una corrección a 4 loops, ¿sí? Pero es necesaria para poder hacer la reconstrucción de todos estos eventos, y todos estos eventos se reconstruyen a través de una simulación. Esta simulación requiere de las sesiones eficaces, y a través de programas como lo son PITIA, como lo son POHEC the Box, generan la reconstrucción de estos procesos. Esa es la importancia de la sesión eficaz que calculamos para poder hacer la construcción o calcular las sesiones eficaces de estos posibles decaimientos de Higgs, que posteriormente son comparadas con los métodos de detección, las sesiones eficaces calculadas en los métodos de detección directa. ¿Cuáles son los? Aquí obtenemos, una vez tenemos este cálculo de la sección eficaz y ya se tiene la reconstrucción de estos procesos, lo que se procede a hacer es a calcular los posibles breaching ratios de decaimiento de Higgs en materia oscura. Como ya había dicho al inicio, no se han detectado, o sea, no hay una discrepancia en los datos estudiados con lo que predice el modelo estándar. Entonces lo que se procede es a derivar los límites superiores de posibles decaimientos de Higgs. Aquí podemos observar en este plot lo que son los posibles canales de decaimiento y los límites superiores de posibles decaimientos de Higgs en materia oscura. Nuestro canal de interés, el que es estudiado por el CM, es este que está acá. Estos son fusión de gluones, fusión de bosones vectoriales. Esto también es una fusión de bosones. Y acá la cuestión es que SMS, cuando hace esta predicción, considera los dos canales que les dije en un principio. Mientras que Atlas, en esta gráfica, sí especifica solamente el canal de producción, este que está acá, ¿sí? Que es este que está acá, donde nos dice que no más del el 0.32, con un 95% de confiabilidad, el 0.32 de los decaimientos de Higgs pueden transformarse en invisible a través de este canal de producción, ¿sí? Como perspectiva futura, se desean estudiar los modelos que extiendan el modelo estándar y pues el acercamiento más sencillo, en teoría, pues es el Higgs portal, ¿sí? Donde considera las extensiones para los 3 diferentes tipos de materia oscura, ¿no? La materia oscura escalar, la materia oscura bosónica y la materia oscura fermiónica. La idea es como en un futuro poder hacer el cálculo efectivo ya de la sección eficaz de estos procesos como tal, de este proceso como tal, de este vértice que está acá, ¿sí? A través de este modelo, a través de este modelo. Y si es posible, pues hacer lo que es la reconstrucción como tal con estos programas que tienen su propio entorno y poder reconstruir como estas gráficas para poder abordar pues no solamente este tipo de modelos, porque este es el que se estudia en el LHC para buscar los posibles candidatos a WIMPs, ya sea de Majorana, ya sea escalar o ya sea bosónica. No, lo que podría generar así como una confusión es el loop no relaciona un cambio en el, no anexa una contribución negativa a la amplitud de probabilidad. Lo que puede generar pues sería como la interacción, como quien dice, el cruce entre estos dos, pero son gluones, no son fermiones. Entonces no genera como una contribución negativa a los diagramas, ¿sí? Estos dos, cuando tú haces acá, primero, los estados de polarización tienen índices de Lorentz mudos. Entonces yo puedo reescribir estos estados de polarización de igual manera como aparecen acá, ¿sí? Y si yo hago una simplificación, si yo reescribo los momentos de loop, si le hago un sweep en términos de los momentos externos, puedo reescribirlo como el resultado que está acá, ¿sí? Entonces no se genera esa, no se genera esa anulación. Uno pensaría que se podría anular, pero no se genera esa anulación cuando uno hace el cálculo directamente, cuando aplica el álgebra de Dirac específicamente. Cuando tú haces el álgebra de Dirac sobre cada uno de estos procesos, porque este es el de uno, pero el del otro quedaría como un momento acá como negativo, este quedaría positivo, este quedaría negativo, los momentos de luz quedarían negativos, y cuando aplicas este momento, cuando haces el álgebra de Dirac dentro de la traza, te das cuenta que da exactamente la misma contribución.
En inglés está bien.
Okay, so our next speaker is Santiago Garcia from Universidad del Valle.
Okay, thank you so much, Professor Carlos. Thank you to the organizers for allowing me to present this talk. I talk you about the recent research that I was performing on the Universidad del Valle, dynamical instabilities in the generalized ACU Proca theory and challenges for cosmic acceleration. The main motivation to study this kind of models is because these kinds was studying before on neutron stars, on particle physics, and mechanics to generate inflation. That is our main motivation, because we want to know what happens if we consider to extend this process to dark energy effects. The first is to consider the full Lagrangian. The Lagrangian consider the most symmetrical case based in vector fields with an additional symmetry in SU2. The additional symmetry is based because these models usually work on particle physics, and it works previously in the models that I mentioned. But the first case that we study is in the easiest case, is with the Friedman Lemaitre Robinson Walker background, and in particular case where the field keeps this symmetry, that is the cosmic trial, that it doesn't have a counterpart in the Proca theory, because in the standard Proca theories we only have a temporal part to keep the background effects. In this case, we could consider the spatial part because the rotation in the spatial space could complement the spin rotation. And consider some additional things in the tensor perturbations. For example, don't allow to keep Laplacian instabilities or Gauss phantom behaviors. We had these restrictions to the free parameters, and we could redefine the coupled constant with the S2 group with these terms. This Lagrangian, this is in PDF or the PowerPoint? Sorry. Could we work in the PowerPoint? Is because well, is this the presentation is wrong in this manner? Could I put my computer? Okay, that's the problem. Okay, well, sorry for the noise there. Behind of these pictures, we had the Lagrangian simplification, and we get exactly the standard Friedman equation of the background. That is the Friedman equation that this restricts to the density needs to be positive, and the second Friedman equation that say how could evolve the rate of expansion. And here we get the equation of motion of our field. And the density and the pressure of the vector field is described like this. Another configuration that we do with the free parameters is to redefine the alpha 3 and chi 5, because if we rewrite in terms of C1 and C2, we reduce the free parameters from 3 to 2. So it's easier to describe the dynamical system, well, the phenomenology in terms of these parameters, because we have less degrees of freedom. Well, the next natural step is to try to restrict more these parameters in order to get the a proper cosmological evolution. And as we want to search for accelerated spatial behavior, not necessarily dark energy, we could also search for inflation. We write the dynamical system in terms of this. With the first Friedman equation, we can write C in terms of X and Y. That is the first Friedman equation. And the second Friedman equation, writing in terms of X and Y, get like this, where we define the new parameters P and epsilon, where P is the second derivative of the field, and epsilon in inflation is now like a slow roll parameter, but if we are in the dark energy scenario, it's only a parameter. In terms of these variables, the dynamical system is so simple. It's on S prime and Y prime, but here we had some problems to describe the dynamical system because this dynamical system is not compact, as we will see on when we find the fixed points. To find the fixed points is relatively easy because, well, the Y prime is exactly 0 when X is equal 0. I need to show something there. Well, I will say you with the iron words. We could solve these equations relatively easy in terms of X equals 0, and we have 3 kind of points. These 3 kind of points, we have 2 symmetric parts because these equations are symmetric in J squared. So we have the plus and minus terms. When we get these parts, we get some point A that it generates always accelerated expansion. The equation of a state it's equal -1. The other points are really similar. That some of them are like reflection, but they don't generate accelerated expansion everything. So if we search for when these parameters can generate accelerated expansions, we get this kind of graphs in terms of the parameters C1 and C2, where A plus 1 is the region where the equation of state is exactly -1 and kernel sets. And this region is when the equation of states is less than -1/3. But this region, if we make zoom in this part, we get that the C fixed points could exist. A particular of these fixed points is that when they generate accelerated expansion, they are attractors on the dynamical system and the stability. That means that the system tends to evolve to the fixed points. That means that it could be a proper dark energy scenario, but we need to analyze if it could restrict the all behaviors to have this kind of phenomenology. So if we study, for example, for the fixed point A, we get that the density that is described like this in the region where this is positive, we need to satisfy this equation. That is C1 negative and C2 need to be greater than this line. So the density is positive, it is in the region B. That means that if we have the fixed point A, we can't to generate a proper fixed point because we are violating the weak with energy condition, because we need to, the density needs to be positive, because if we don't respect this, we will have a rate of expansion complex, and that doesn't make sense. The problem with the other fixed points B and C is that if we test exactly when the system reaches these fixed points, the density goes to infinity. So they are not bounded. So the question now is, what could we do to try to save the model and analyze a more proper description to describe the cosmic evolution? Well, as the system is not compact, that means that there are more than one attractor. There is not only one global attractor. That means that we could analyze something that is called pseudo-stationary state or null clines. That means that we don't need to consider that the full dynamical system is equal to 0. We are not analyzing exactly the fixed points. And so we will consider some particular fixed points where only one of the equations is equal to 0. So when we analyze these equations, we know that when x and y tends to 0, this could be tends to a straight line. So we could try to plan to that solutions. When we plot the phase space, it's easier to look this, but we suppose that we consider that solution. So if we take this kind of solution, this is a particular solution that the second derivative of the field is proportional to the speed of the field. And if indeed, when the system is over these straight lines, the Hubble rate is constant. And this is a particular case where that it's called constant roll. But the article that I previously mentioned is constant roll inflation, but this could be constant roll dark energy. And if we suppose this kind of solutions and make y prime equal to 0 using this solution, we only need to solve this case. And we consider the case when x and y are huge, really huge. So we make x tends to infinity, and we get this polynomial equation. And we can get 3 slopes to the straight lines. Obviously, in this case, the procedure is the same to do for the simplest case to the complex case. Because, well, if the model doesn't work for this, the same procedure we could demonstrate for this case. But in this case, we would like obviously to search for the case when the equation of states could generate accelerated expansions. That means that this equation need to be less than -1/3. And if we study, for example, this and analyze the phase diagrams on a particular solutions, when in the previous article says that the inflation case could have a successful ends that it's with the initial condition and these parameters, we get these phase diagrams, and this is the straight line that we predict. That is like an attractors region that if the x and y are huge in the initial conditions, the system always tends to keep the straight lines. But it changes when x and y tends to be really small. The problem here is that in the dynamical system, when y tends to be so small, it's an essential singularity of the system. So we should to analyze this case that it's called the central zone in a different manner. So if we do the same procedure with the straight we did with the straight line, but in this case solving x prime equal to 0 when y tends to 0, that is this essential singularity, we find that a pseudo fixed points at plus minus 1, 0. That is O minus and U mass. And we could do the standard procedure to the dynamical system to analyze what is the stability of these pseudo fixed points. And we get this is the eigenvalues and the eigenvectors. For the U minus, we get this. So if we approach to the point over y positive, we get this is negative, and this tends to minus infinity. So this is a saddlet. And the same procedure to this, we get the same. This will be a saddlet too. And then the system tends to be oscillating over both of these points. But the problem here is that the systems in each stage during the oscillating, the wave value tends to become more and more small. So it's approaching to the essential singularity of the systems. And when numerically it reaches the essential singularity, it escapes of the central zone. So it can't describe a proper end of inflation because, well, we could predict how long it could to take to end to decay the field until reach the central zone. But it only depends on the initial conditions. If we set this only taking this into account, we get that it could reach on the thing that we how to reach the inflation time. That well, it depends here. If we plan to integrate the time to take the taking into account the rate of expansion that we could write in terms of this, I integrate the if-false number that it needs to expand at least 60 if-false. We could set this in terms of the initial conditions. But when the system reach the smaller values, it reach a singularity. This is the first singularity that the system reached. And we could look this in observable values. For example, in the slow roll parameter, we reach that when we reach the first time the singularity, we had a peak. So we have a peak in a singularity on observable value. So that means if we had an analytical solutions, this could be a state function. And then when the system tends to oscillate and the solution will be analytical, we will show that these solutions tends to oscillate and stabilize in y equal to 0. So the observable values tends to be infinity. And we know that it doesn't hence because we are not saying that the rate of expansion is this moment, it's infinitive. So this system is highly unstable for inflation. So the question now is, well, in inflations, that means that it doesn't work so well. And what happened when we study the dark energy scenario? In the case of the dark energy scenario, we could do the same process, but analyzing another singularities. Because, well, in theory, when we consider the inflation case, we expect that the fields decay in the during the time that we hope to explain inflation. But during the dark energy, we hope to it allows to have the dark energy, the radiation and matter domination, enough time to form the structures and observe all observables that we have. But so the field needs to keep in this central solve and then goes out on the other straight line and the field becomes greater. Well, if we try to do this, start on in the central zone, we will see that it will oscillate in the pseudo-fixed points and then will escape. It will escape over the y equal to 0. And well, in the y equal to 0, we know that this is an essential singularity and it doesn't produce accelerated expansions. And we could try another solutions to search, for example, what happened, well, all solutions could oscillate or there could be another solutions. So if we search, for example, with the X prime, where we get some kind of singularity 0/0, we get that the system starts on a huge number, but sadly, when it reaches the points where we satisfy these equations, the system crash and the systems can't evolve. And the problem here is that the all pseudo-fixed points has the behavior as an attractor. So the system is highly unstable. Well, in the inflation case, we had an unstable oscillations and the escapes and don't allow to connect with radiation epochs. And with the dark energy, we had that it could oscillate, but this is very fast and don't allow to start a matter domination because when it goes out from the central zone, the density tends to infinity. So in resume, using this kind of model based on the more general vector fields with the symmetries, it's not possible to describe a proper a fluid that makes accelerated expansion of the universe because the weak energy condition is not satisfied, the system is highly unstable, and it's not possible to predict the full cosmic history for all these complications. Well, something that I want to discuss this is not only to keep in mind that the model is not work. I would like to recast that the method that we use to demonstrate that the system is not possible to describe a cosmic history is that it's not, if the dynamical system is not enough to constrain, we could apply another method that is study what happened with the pseudo-stationary stars or nucleons. That it's if the system is not compact, that means there are more than one attractors that we can search for what is the behavior that these unstable situations that generates our chaotic scenario could perform in the phase diagrams and the numerical solutions. Answers what happened in these scenarios and if it will possible to constrain more in these cases in some of the pseudo-fixed points. Well, that's all.
So I didn't see if you consider this bit the tensor dual, the dual of the tensor terms. Where are
Mhm.
them?
In what the alters? Well, in this case, we consider the all possible contribution of the vector fields, that is the standard Jan-Mills, and the vector B, and A, that is the construction of the symmetry and asymmetry part, that is the plus and, well, and the rest part of that. And we fix the couple constants to keep the maximal symmetries of the spacetimes. Okay, I don't know.
So it seems you consider B tilde.
Hmm?
So it seems you consider B times B tilde.
Yeah,
Okay.
yeah, that is considered.
Thank you, Professor, and thanks to the organizing committee for letting me give this talk today. What I'm going to show you today is basically some of the results that we are going to present to a physical review D paper during the following weeks, which has been brought part of my PhD thesis. Basically, what is the scotogenic model? The scotogenic model is a model to generate neutrino masses at one loop. Basically, the original scotogenic model, what does is to add a set 2 symmetry under which the dark matter particles have charge -1, whereas the standard model ones have charge +1. What's the difference right now? That we add this sigma field, which is a singlet scalar, and due to its set 2 charge, it is allowed to mix with the standard model Higgs. So basically, the standard model leptons only can couple to the dark sector via one loop Yukawa couplings. Those Yukawa couplings are generated by this Lagrangian, this first term in the Lagrangian, and the sigma is used to generate the Majorana masses for the Majorana fermions from the scotogenic model. Basically, this sigma field breaks global symmetry, a global U1 symmetry, which is usually associated to lepton number. And after that, its spontaneous symmetry breaking generates Majorana masses. But the complicated part of the phenomenology is that the potential is really complicated in contrast to the remaining models that we saw today. Basically, we have a mixing between the standard model Higgs doublet and the singlet. Basically, we can see this here after we do a parametrization around the SU2 vacuum expectation value. Here we have the charge Goldstones, H and eta plus, and we have the neutral Goldstone bosons, which are pH and p sigma. When we take all this parametrization and replace it here in the potential and take just the quadratic terms in the Higgs scalar and the sigma component, we get these two masses here in equation 4 and 5, which seems that we are getting massive Goldstone bosons and also a mixing. But when we apply the tadpole conditions, which are basically starting the minimum of the potential as a function of both H0 and sigma, we get that we still have massless Goldstone bosons, which we could identify with the standard model one, which gives the transverse polarization to the set boson. And we have a physical remaining state, which usually in literature is referred to as the Majoran. However, after applying those conditions, we see once again that the mass is still non-diagonal, meaning that we need to diagonalize to switch to the mass eigenstates for the H fields. And we can do this by a usual SO2 mixing matrix. Now, after this part, as in a similar fashion as Professor Diego explained, neutrino masses are induced or are generated by a one-loop correction, which in contrast, now we have this additional line here that takes into account the interaction with the sigma field. Okay, the neutrino mass matrices take the usual scotogenic fashion. And now what we wanted to do is to study the collider feasibility of this model. To do this, we had to consider both dark matter scenarios. We have a scalar, which would be the lightest of these fields, could be either a real scalar or the pseudo-scalar. For the sake of this part, we consider the pseudo-scalar. Or it could be the lighter of the Majorana fermions. How do we couple these things with the theory, with the first part of the experimental data? Is by the means of what is called the Casas-Ibarra parametrization, is basically connecting the Pontecorvo-Makina-Kagawa-Sakata matrix, the measured values of the neutrino oscillation data, with the loop function, which usually in the type 1 seesaw mechanism is just the Yukawas. However, we need the model to be able to explain all these constraints, or to follow these constraints. To do this and to map all the parameter space, we used the Markov chain Monte Carlo algorithm by the means of a software called Spheno. And also, after passing through Spheno, we use micromegas to calculate the values of the relic density, which can be seen here in this figure. Here, we see the 3 peaks. We see 3 peaks because we considered first 2 MH2 scenarios, basically 246 GeV and 500 GeV. And we see also the peak at half of the standard model Higgs mass. Here we have 2 colors. One is for basically fermionic dark matter, which is the bluest one. And here we have a small portion of cyan points, which are the pseudoscalar. Okay? One thing that we also wanted to explore, this stopped working, it's working, is we analyzed this data for 3 different vacuum expectation values just to see how the parameter space behaves. Basically for 1, 3, and 9 TVs, we still have the same fashion. However, for a value of 9 TV, we have that some of the solutions go up, okay? This is without imposing any conditions between the masses of the fermion and the mass of the lightest scalar. And in this condition, in almost all the simulations that we carry on, 89% of the points are associated with fermionic dark matter. However, when we impose that the mass of the fermion and the mass of the lightest scalar are close, in this case 50 GeV, we see that the distribution of the points kind of balances out. And in particular, here we observed that we had a 56% density of points related to fermions, and the remaining part is associated to scalar. So why do we do this? Because usually when these kinds of models are, one of the things that we wanted to do is, well, probe these sort of processes at a collider, such as the LHC. And when we analyze the decays of the etas, the eta scalars, they usually go through a neutrino. As you can recall here from the Lagrangian, right here, it says goes through a neutrino and a charged lepton. And as the 2 of them are really close in mass, we have what is called a compressed mass spectrum, which is usually analyzed in supersymmetry models. Okay, so what we did is trying to consider different compressed matter scenarios and see the impact of those scenarios in the cross section. Okay, to do that, in the case of fermionic dark matter production, as it does not couple directly to the standard model gauge bosons, we had to consider an intermediate charged production. Basically, it's saying that these 2 etas are eta plus and eta minus, whereas, and allow them to decay via the Yukawa that I just mentioned before. We consider the 2 MH2 scenarios that I told you, and several vacuum expectation scenarios from 1 TV to 9 TV, and 2 different compressed mass spectral scenarios of 20 and 50 GeVs. In particular, we focus on the 50 because it's the one that has more cross-section data obtainable from CMS and Atlas experiments. Okay. After doing this, after choosing all these parameters, we implemented the model in Fine Rules, which is a tool that allows us to do calculations in MathGraph, okay, and calculated basically the cross sections. Among all of the possible states that we had, one of the first things that we did was to check which were the intermediate topologies, which were the intermediate channels of production. And here we have here on the right the dominant channel for scalar dark matter, for fermion dark matter, and here for scalar dark matter. What does it mean? Basically that we here directly, here on the left, we directly produce the dark matter candidate. And then what we have to allow is the eta R to decay into standard model particles. And in this case right here, if you go again back to the Lagrangian, we will have two soft leptons, which is basically what I show right here. So we passed all the spheno points through and micromegas compatible points through MathGraph. And the first thing that we saw, as you're going to see in the next slide, is that the cross-section, as we have a lot of vertices, in particular, these ones right here and right here, the cross-section, as we have a scan, as we have a Markov chain Monte Carlo scan, which is random, the cross-section exhibit a high variability. Okay, so we needed to have some sense of control within it in the data that we have. So basically what we did was we introduced this parameter beta, which is basically the ratio between the full decay of the cross-section over what we would call the intermediate topology. So basically you can see that this is basically a term that's related to branching ratios and interference terms with additional Feynman diagrams in the process. We took the maximum and minimum values of this beta distribution for both dark matter candidates, and we obtained this band right here. I don't know, you can see the gray part properly? Okay, basically what we obtained is that all the cross sections fall below like 10 to the minus 6 picobarns up to down to almost 10 to the minus 22. How do we know that these cross sections are feasible or not? Basically, in this case, for the scalar sector, we considered 1.69, basically 95 confidence level, significance for 3 different luminosity scenarios, and calculated the cross-section obtainable within a very optimistic scenario, just 20% background, 20% systematics, and 10% acceptance, taking into account that the usual collider study has higher backgrounds and lower acceptances. And if you check right here, from neither of them, the band crosses up. So basically, we could say that via Drellian mechanisms, scalar dark matter within this U1 scotogenic model cannot be probed at the LHC. Okay. What can we say for the fermionic sector? For the fermionic sector, what we did was some years ago, the Atlas experiment carried out a similar study in the context of SUSY, similar final states. Basically, it's 2 soft leptons and a huge amount of missing ET. And they carried the study at 139 inverse femtobarns, as we have the same final states. The limits on the cross sections could be extrapolated to this case. However, not all the limits on this case were extrapolated, such as the ones from the delta M's on the compressed mass spectrum, because here they have same flavor leptons. We can have lepton flavor violation in this model. So as you can see here, we have a tiny region of parameter space that falls within the projected sensitivity that we calculated for the high luminosity scenario from the LHC. So we could say basically that it could be probed for masses around, let's say, 150 and almost 300 GeVs. However, there's another possibility, is basically that these 2 etas are neutral. And one way to probe it was proposed many years ago in the LHC, but it's basically vector boson fusion. Basically, what we would have would be 2 purely missing transverse energy, or basically 2 dark matter candidates along with two QCD jets, with what's called vector boson fusion jets. And what we found here, when comparing to CMS data from 2019, is basically, whereas in the Drellian case, there was some phase space to measure dark matter, now it's the opposite. In the scale, now we have some parameter space to measure the scalar part of this model. Here you can see for this high luminosity scenarios, okay, within 300 inverse femtobarns and 3,000 inverse femtobarns. Okay, so just to make a small review of my talk. So what can we say? As I just mentioned, scalar dark matter cannot be probed at the LHC via Drellian mechanisms due to very small cross-section values, whereas the fermionic just has a very tiny parameter space compatible. Whereas in the case of vector boson fusion, it shows some complementarity, whereas in one case, fermionic could not be probed. In this case, fermionic scalar is the one that can be probed. Okay, thank you very much for your attention.
So Eduardo just told me that we need to hurry up and there's no time for questions. So, but in any case, Gustavo will be available during the rest of the event to answer all the questions you may have. Okay, so let's thank Gustavo again and proceed with the next.
Well, thank you. Hello, everyone. I'll show today partial results on our work on effective models for two-component scalar dark matter with C8 and C10 symmetries developed alongside Diego Restrepo and Amalia Betancourt. So we're tired. We need to do this quickly. So just the model. We propose a two-component scalar dark matter charge under a C2n symmetry. It contains a complex field phi A and a real field phi B with associated charges that you can see in the screen. At the very least, a couple of you will be very familiar with a previous work by Laguna and Zapata on this exact same construction. One of the results for that work was that potentials for C8 and C10 lack new terms. With that in mind, we extended C8 and C10 scenarios to include effective operators of up to energy dimension 6. The tools we use are fairly standard. SIM2INT can produce the Lagrangian terms for a given set of fields and symmetries. With Feynman rules, we can take set Lagrangian and calculate the Feynman rules. And with those Feynman rules, we can use micromegas to calculate DM observables. First, we construct a single component case in order to construct the two-component case later. And you can see here you can see the terms of the Lagrangian that we are interested in at this moment. Here, m is the mass of the dark matter particle. Phi A or B is the field of dark matter particle. And whenever we say phi A or B, it means that this is true for every C2n, for every 2n, I mean. And here, H is the Higgs doublet. To the left, we have the real case, and to the right, we have the complex case. This result is not completely new. Juan Criado and others already produced the plot for the real case. However, the complex case they did not produce, but it is fairly similar to the previous. Now, we combined both of these two single component cases to create a two-component case with these relevant operators. To the left, we fix the parameters associated with the complex fields. So we explore the parameters of the real field. And to the right, we do it the other way around. We can already see that the scenario changes. However, we also defined the proportion of dark matter for each of the fields. And in this case is more telling, since we can already see that changes in one of the parameters of any of the fields produces changes in the abundances of both dark matter fields. With this, with the last case as a base, we start adding more effective operators that explicitly mix both dark matter fields. Firstly, we add this term in red, The red region, in this case, represents where the effective field theory for this term breaks down. The black region represents the breakdown of these operators. And we can already see differences, but the proportions are more telling. In the presence of this operator, the lightest dark matter particle always dominates. Now, for the operators produced by specific SLIT2N symmetries, we start with the CN case, CE8, excuse me. The new operator allowed, but the symmetry can be seen in red. And seeing these plots alongside the proportion, we notice no difference comparing with the results without this term. For C10, the results are analogous, and we do not see noticeable differences in the parameter space or in the proportion. This does not completely rule out that these operators can produce an effect. However, we will need to explore more the parameter space by performing a random scan to be completely sure that there is no configuration that can generate the interesting effects. And as a conclusion, partial conclusion of what we have until now, we have generated correct dark matter abundances for single component real and complex dark matter with effective operators. We constructed a two-component scenario combining both real and complex fields, effective operators such as this one and this one that are general to every C2N symmetries, change the outlook for generated correct dark matter abundances, and operators specific to C8 and C10, this one and this one, do not seem to meaningfully affect the dark matter abundances, but more work is required to completely rule out their effects in this case. And these are the references, and that's the end. Thank you very much.
Okay. So thank you very much, Simon. And as I said, there is no time for questions. So let's thank Simon again and all the speakers who participated in this afternoon session. So we have some words here.
Okay, today, you know, the welcome is at the Teatro Imperial. Then this is in the carrera 26 con calle 14, is more or less. Los estudiantes que hablaron con la profesora Carla acerca del alojamiento, por favor que se pongan en contacto con ella, ¿ok? Entonces, si ustedes les dicen a un taxista que lo lleve al Teatro Imperial, cualquiera lo lleva, ¿ok? Entonces, nos vemos ahí a las 7 en punto para la bienvenida. Por favor, llegar puntual, ¿ok? Bueno.